Alright everyone, well welcome to the last lesson in this unit on wave, sound, and light. This is the lesson on light. This is also the last video lesson that you're going to actually be getting from me like this in front of my TV for the year. This is the last thing you'll be taking notes on. So let's just get started. So first off, what is light? And if you get the song reference, you'll understand the title that goes here after this. So light is basically two things all wrapped in one. It's bipolar. It's got a dual personality. Light is a particle. So think of like a tennis ball bouncing off the floor. You know, light reflects off of a mirror. So think of that light bouncing off the mirror as the light is a particle. This is what Einstein figured out in 1905. This was one of the things that he did in 1905. He was kind of busy that year, created three huge theories. One of them got him the Nobel Prize. He had some time to kill. The other thing is light can act as a wave. So, you know, like the transverse waves that we've been talking about all along, light can be one of those. Light is not longitudinal, because remember, a longitudinal wave needs something to travel in. Light doesn't. A way to tell that light is a wave is if you have a pair of sunglasses, and these are polarized sunglasses. Not all sunglasses are like this. And how you know it's polarized is if you take it, let's say you're in your car, you hold the sunglasses up, and you rotate the sunglasses 90 degrees. And you can kind of see right now. So look through the sunglasses through the screen. As I rotate my sunglasses 90 degrees, see how it gets dark? And they come back, it's like clear again or clearish again. This is because light is a wave. So what's happening is the light waves coming off the screen are going in all sorts of different directions. What polarized sunglasses do or polarized films, is they allow light to travel, let's say, in one direction only. So if I've got light that is traveling this way, traveling up and down, and these glasses are blocking the horizontal light only, will the vertical light get through? Yeah. So vertical light cannot get through a polarized film that's blocking it horizontally. So it's like acting like a fence. You know, you can only get through a picket fence one way. These are very good for driving because a lot of the glare that comes from the sun through the window off the dashboard is polarized light, and having polarized sunglasses reduces a lot of the glare off of the dashboard. So if we run with this light as a wave thing, you know, when we looked at waves, they could have multiple frequencies, multiple wavelengths. Visible light is a very small portion actually. It's only from about 350 nanometers on the low side to 750 nanometers on the high side. So 350 is the base edge of violet or purple. 750 is the top edge of red. Beyond it, you have ultraviolet, which our eyes cannot see. You have infrared, which our eyes also cannot see. But it's considered light. Ultraviolet light, that is if you ever go to like a buffet or somewhere like that and you see like a heat lamp, sometimes that can be UV. The grow lights that people use when they're trying to grow plants, that's ultraviolet light also. Ultraviolet light also comes out of the sun, so you can get a suntan on a day that has got a little bit of clouds because the UV light can go through the actual cloud itself. And of course, this is what we call Roy G. Biv. So red, orange, yellow, green, blue, indigo, and then violet. How fast is light? It's fast. 3 times 10 to the 8 meters per second. It is the fastest thing in the universe. Nothing can go faster than light. That's it. That is the universal speed limit. This is why when there's a thunderstorm, when we've had a couple of them rumbling through in the past week or so, you see lightning, then you hear the thunder. Because they're both produced at the same time, but because the light is traveling about 1,000,000 times faster than the sound, the light reaches us first. So how does light interact with materials? So now we're going to go through kind of how does light actually behave. So the first one is what we call transmit. So I have some sort of material, a light wave hits it, then what does it do? It goes through it. This is transmit. What transmits? Glass. Clear glass transmits 100% of the light that goes through it. If you have like wax paper that's sitting around, and you kind of hold it up, or even a standard sheet of paper, and you hold it up to the light and you see light going through it, most of the light is being transmitted. And it's actually, what it's also doing is actually diffusing some of the light too. So it's not just focusing it very sharply, but it's actually kind of diffusing it outwards. The other thing that can happen is light can reflect. So I have another object here. I have a light ray that hits it, then a light ray, that same light ray bounces off. Now a good example of reflection is of course a mirror. Light hits it, and it bounces off. Mirrors that were created about 100 years ago, if you look at it, they're kind of tarnished, so there's like black spots on it. That's because the mirror was legit like a piece of glass, and they took silver, silver like the metal you'd see in jewelry, and actually encased the silver in some sort of like a paint, so they can paint it on the actual glass, and that was the original mirror. I'm going to show you an example here of both of these. This, if you can see it, this is what is called an infinity mirror. And if you kind of see as I turn it around, I've got some lights here behind it. You see the reflection on it. There's only one row of Christmas lights here, but when you look at it from the front, it's like it goes way, way, way deep down in there. What this is doing is it's a combination of the two. This piece of glass on front is called a half mirror. So what it does is it does half transmit, half reflect. So when the light from one of the little lights, the little Christmas lights, is bouncing through here, when it hits the front piece of glass, half the light goes out, half the light reflects back. The piece of glass in the back, this is just a normal mirror. So all the light that hits it goes out. So what's happening is light from one light bulb, let's say it hits the back mirror, all the light goes reflected forwards. Some of the light goes, half the light goes through, the rest of it comes back. Then it hits the back mirror, hits the front mirror again. Half of that light goes through, half of it comes back, which is why you slowly see the intensity dropping off as if you were to kind of be staring deep down into it. A lot of optical illusions, like magic tricks, are really done with mirrors, because there's interesting ways you can make it look like people actually float. One of the great magic tricks was a guy looked like he was actually floating, and he was actually standing with like his legs apart, and there was a mirror right between here. So he had one leg behind the mirror standing on the ground, and the other leg was in front of it. The reflection made it look like there was actually like some mirrors there, like he was actually floating. I also just watched a thing on YouTube that the Hollywood Tower of Terror at Disney in Florida, some of the illusions that they use before you start riding up and down, is actually used by projecting images onto panes of glass. And that's how they get this like depth perception thing going on. It's really trippy. The other thing that light can do is it can absorb. And absorption is kind of based on color. So I have this green panel here. Why does it look green? Because out of the colors of light that hit it, what happens is I have red and yellow and green light going at this little green pane here. Because this is green, it is reflecting only green. The color is red and yellow. They are getting absorbed by it. So it's like they just go and just stop. It's like a sponge. But the green reflects out. This is why now you see like people, if you go to the store, you can buy different types of LED light bulbs. You can buy the daylight, the cool white, the off-white. All those different colors of white have different like reflectivities and different absorptions of different colors in the spectrum. There used to be an older light bulb called like a GE Reveal light bulb. And what that one did is it actually, the glass of the light bulb itself was colored in a way that it actually reflected, it did not allow yellow light to go out. This yellow light kind of makes things look kind of like not so bright white. The other one that you can have is what's called scatter. And scatter is like if you take a rock and you kind of, if you go to the beach, not now, beach closed, you get yourself a nice flat rock and you kind of whip it at the surface and you can get the rock to actually skip. That's an example of scattering. And every time the rock kind of hits the water, you see some ripples. What's happening is there's some energy being deposited in the material itself. The energy of a wave is directly related to the frequency of the wave. So this wave, here's the red one, this actually has a higher energy than this blue one does. A neat way of seeing scattering is if you have a laser pointer, so, laser pointer, and then you have some sort of like spray. I'm going to give this a shot here. So, if you watch the laser pointer here, I'm trying to shine into the camera, and if I spray the no stinky spray, when I taught freshmen, I would go through like 4 cans of these in a school year. You can actually see the laser beam. It's actually causing it's very Febreze air here right now. You're actually seeing the laser beam actually scattering off the particles. So when you see like there are some like sci-fi movies that you're trying to do like some jewelry heist, what they'll do is they'll go through like with smoke cans, because then they can actually see the laser beams or the IR beams or whatever sort of beams are there. If they have IR, they need special glasses so they can see them. But to try and see the beams that are there for the like burglar system. Ooh, stinky. So how else can light interact with the material? Well, it depends on the material itself. So there's what's called transparent, translucent, and opaque. And all this is based on light being transmitted. If something is transparent, all the light goes through. Now, it can be transparent for a color. For example, stained glass. So if you have a piece of glass and let's say the glass is red, the glass itself is actually like red. So what's happening is it is transmitting red light, but blue, green, yellow light, all that's being blocked, all that's being absorbed by it. A hybrid of, then you have, let's on the other side, let's go to opaque. Opaque, well, nothing gets through. A brick wall is opaque. Light no get through. A hybrid of the two is translucent. So some light gets through, some light is transmitted, some light is absorbed. And like wax paper, a sheet of paper, newsprint is kind of very thin. That is considered translucent. Now, with all this talk about color, how do we actually see color? We're going to talk about the human eye for a little bit here too. So the visible spectrum of light, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. What is missing off of there is white and black. Why? Because technically, from a physics perspective, they are not a color. It is the amount of colors that are being either reflected or absorbed. White is where every single wavelength is being reflected. So if I have a sheet of paper here, this sheet of paper here looks white. Because of all the light that's coming through, what does it do? It goes, it hits the sheet of paper, and almost all the colors are being reflected back out. If you have something that's black, all the light hits it and is being absorbed by it. So this is where clothing comes in, especially for ladies. Everyone tends to wear lighter colored clothing in the summer. Why? Because it's hot. We want to stay cool. Lighter colored clothes reflect more light. If the light is being reflected off, it is not being absorbed by our bodies, so we don't get warm. In the winter time, when it's colder, everyone tends to wear darker colored clothes. So what happens is when you're outside, if you're in the sun, you wear darker colored clothing, so instead of reflecting the sun's light rays, you actually start absorbing the light rays to keep you warm. Another good example of this is in Southern California. It's a lot of concrete, gets really, really hot. Certain pavements you can actually like crack an egg and cook it. Why? Because the pavement is black. And what does that do? It actually makes the street and even where you're walking a lot hotter. It's called the heat island. This is one reason why if you look at the Chicago temperature patterns in the summer, downtown is always warmer. If it's really, really hot, downtown is going to be warm. The lake will keep it cool, but the concrete in the buildings are going to actually help heat it up. So what they started doing in Los Angeles is they started doing some sort of a gray paint. They're painting the streets to go from a black asphalt to kind of like a gray, like my hoodie color. And what is this doing? It's actually helping to reflect the light to keep the sidewalk a lot cooler and keep the air right above the sidewalk cooler also. Now, how do we see color? So, if you were to take your eye apart and dissect it, you're going to see there's a receptor cell called a cone. And we have cones that are in packets of 3. So you have a red one, a blue one, and a green one. So when you see the color red, the red receptor cone is activated. When you see the color green, the green receptor cone is activated. When you see orange and yellow, it's a combination of the two. So orange is more red, a little bit of green. Yellow is about a relatively even mix of the two. So if something looks yellow to you, your red and your green receptor cones are both being activated, but also possibly at different rates, at different amounts. That's how you see color. So when someone is colorblind, it's not like it's either like colors or grays. People can be colorblind to very specific wavelengths. So reds may look kind of greenish, or they might look kind of more brown. Violets might look a little black. Because, why? It's just the way how their eyes are. It's just the way how their colorblind is. It's not an all or nothing. This is why, when you drive down the street, next time you go, look at the stoplights. Every stoplight in the United States is red, yellow, green. Why? Because if someone is colorblind, if they can't tell that it's a red light, but they know that, okay, there's circle, 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 they know the top circle is actually bright, you know it's stop. If they see the middle circle is lit up, they don't know it's yellow, they go, oh, it's yellow, I have to speed up. Also, look at, next time you go outside, look at all the street signs. You know, they tell you like, Pulaski, Cicero, Lawrence. What color are they? They're all green. You know why? Because where is green here? Smack in the middle. So what? Our eye is most sensitive to the color green. So the green background with the white lettering is a high enough contrast for, regardless of if you have any sort of color blindness issue, you can actually make out the writing. Also, if you have a laser pointer, you can get, this is a red one, you can also get a green laser pointer. It's the same power, but it just looks a hell of a lot brighter. Why? Because our eyes are sensitive to green. Now let's look at how this TV works. So TVs, Jumbotron displays, you know, this is at a sports arena which is now closed, are actually packets of little pixels of colored LEDs. This is an LED TV, so it's little pixels of LED. And they come in bundles of red, green, and blue. Because what are we doing? It's called color mixing. So if you were to look, let's say with a microscope, really closely at this TV, you're going to see a little packets, they probably don't look exactly like this, of red, greens, and blues. And they get fired in different amounts to create different colors. So red and green light makes yellow, red and blue makes magenta, blue and green makes cyan. Now this is light. This is light. Mixing colored paints is different. So taking like red and green paint together, you kind of get like this poo-poo brown color. That's for mixing paints. This is mixing actually light. So red, green, and blue make white. So for theater productions, they have all the lights above them. If they need specific colors, they don't buy light bulbs of that specific color. What they can do is they can use maybe several different colors of lights and overlap the beams on one another to make any color that they want. All they have to do is vary the intensity or the brightness of each individual light bulb. So this is called color addition, so that's adding light. Color subtraction is when you're adding paint. So if you have an inkjet printer at home and it's a color printer, you don't have little cartridges. It's not like a box of Crayolas where I have 128 colors, 128 crayons. No, you really generally have 4 cartridges. You have a black one, a cyan one, a magenta, and a yellow one. Why? Because those are the only colors you need to make the rest. So yellow and cyan paint make green. Yellow and magenta paint make red. Magenta and cyan make blue, and yellow, magenta, and cyan make black. So if you can tell, when you have 2 of the subtractive colors, you get an additive color back. So for example, this watercolor here that my daughter and I made. Very, very good. But you can see, this is the basic set. If you look at here, we have a little bit of the blue and the kind of the orange and the red there. You start getting some of these weird colors here. I don't know what this is supposed to be, a balloon or something like that. You start overlapping them, you're actually mixing the colors together. You're mixing the color paints together to make new ones. If you take any sort of like newsprint, so for example, I have DVD here of Happy Feet. Looks like a full color screen here, right? Well, when they print these, and like in newspapers especially, they may not have one printer that does all the colors all at once. They may take this thing here and actually print it 4 times. They'll print it once for black, once for cyan, once for magenta, once for yellow. And if you need to get a color in between, like the magenta paint goes down first and the yellow paint goes on top of it, so what is that going to do? That's going to give you like a reddish color. It's called a 4-color printing process. It gets run through multiple prints, and then the layers, the paints just keep adding on to each other. If you ever look at an inkjet printer, each ink kind of squirts out like at a time. But the colors are created, the different colors are created because, let's say, the yellow got squirted out first, then some blue got put on top of it, and then that made the green. So that's color addition and color subtraction. The last thing we're going to look at is how kind of light actually works with some other ways of looking at different materials. This first one is what's called refraction. If you've ever gone down into a swimming pool and something drops away at the bottom of the pool, if you do an exact beeline through the water, so you're above the water, you go through the water and you go straight through, you're going to miss it. Why? Because of where the light is. Because what happens to the light is we get what's called refraction. And this is a legit image here. So you have a green wine bottle with 2 wine glasses that are partially filled, and it makes like a hole in here. Reason why is because when light travels through a material, it actually bends. The reason why it bends is it slows down. So this only happens when light's going through a material but at an angle. So if you ever went to like the aquariums, you have like the round fish tank, and some, depending kind of where you are, it looks, the little fish look kind of weird. You see them at different angles, they might look distorted. That's because light is traveling at one speed in air and another speed in water. Light actually slows down in water. Here's why. This is a good example of it. So imagine here you have a sidewalk and you have grass. And you have 2 wheels rolling at it. What happens is, and also they're rolling at the same speed. The first wheel here hits the grass. What does it do? This wheel starts slowing down, but it's connected to this other wheel. So what does it do? Is it starts slowing down, the whole axle starts turning, and it turns enough until both wheels are on the grass, and then they move out. Same thing happens in your car. There's a thing in your car called a differential. And what that does is if you turn your car, if both tires moved at the same speed, you'd spin out. You'd be very, very difficult to control. When you make a turn, and let's say you're turning right, the right-hand wheel, or whatever the turning axle is, turns slower. It rotates slower than the outer wheel. Why? Because the inner wheel has less room to cover, the outer wheel has more room to cover, so it moves a little faster to turn all the way around. That's why if you look at car tires, they get worn out differently, depending on how you drive. So how much refraction depends on the material itself. So air is kind of the base. It has what we call an index of refraction of 1. Moves at normal speed. It slows down a little bit in water, slows down close to the same in glass. So if I have this type of incident right here, I've got light going in. If it didn't slow down, it would go straight through. The more it slows down, the more the light refracts. So the more kind of bent in towards this vertical line. This is what we call a normal line. The bent in it gets. If light speeds up, it actually kicks away. And how does this happen? Generally, when you're going from water, if you're, let's say, sitting in a pool with a laser pointer, it's going to go one way in the water, and then it's actually going to then bend out again in air. This point I make because of a prism. So prisms, this is the most basic prism. It's a triangular piece of glass. And what's happening here is white light is coming in. But because each color has its own frequency, so its own wavelength, the wave is kind of a different size, so they refract more. So that's how you get the rainbow patterns. In a diamond, the more cuts you have, you can get some really nice rainbow patterns if you shine white light into a diamond. This was discovered by Isaac Newton. Why? Because, well, he needed something to do. So he took his science lab, closed all the curtains, carved a piece of glass to make it a triangle, put it there, and was like, oh look, rainbow. And this is how rainbows appear. Because what happens is the water droplets act like little prisms, and you get the rainbow effect. If you're ever flying, which we're probably not doing right now, and you see a rainbow from the plane, the rainbow, what shape is it in a plane? It's a full circle. It's actually a full complete circle, full 360. From the ground, he's not. Why? Because we're not seeing all of it. Now, back to diamonds. Diamonds have something that is called total internal reflection. That is because when you shine light into it, it gets stuck, it gets trapped in there. It starts bouncing around. So this is where fiber optics comes in. So AT&T now has fiber optic cable internet service, much faster internet service. The cable is not a normal cable with a wire in it. It's actually a glass pipe. It's a glass tube. It's like extruded glass. And what happens is the signal isn't electrical, it's optical. It's a piece of light, it's a light beam that goes and it starts bouncing in and out of the cable all the way down until the end. And why does fiber optic cable get you faster internet? Light travels so much faster than an electron passing through a wire. And this is why fiber optic cables, if you have them at your house, you can't really tie them really tight. The lines coming in, if you look at them on the side of your house, have to be held kind of loose, because if you pull it too tight, you can put too much tension on the glass and cause some fissures inside. And then you start losing internet speed and you're on hold for customer support, and you need the internet right now for code on location 2K20. This total internal reflection is why diamonds sparkle so much. Because what happens is, diamond is the one material that slows down light to about 2.5 times as slow as it is in air. So when it slows, it bends a lot. Well, if you cut it, if you put the facets on the diamond, you can actually keep the light stuck inside the diamond. And it bounces around, bounces around, bounces around, then eventually it makes its way out. So what does this total internal reflection mean in terms of a number? There's a thing called a critical angle. And again, I'm just going to focus on diamond here. So from air to water, air to diamond, there's a critical angle of 24.6 degrees. That means that if light is trying to get out of the diamond, and it makes any angle that is somewhere between 24.6 degrees and 90, it doesn't leave, it gets stuck and it stays in. That's what this is saying. The light has to actually make an angle less than 24.6 degrees in order for it to escape. So every time the light kind of bounces around inside it, it's staying in there. And the more you can get the light to stay in there, the more sparkly it is. Which is why different cuts of the diamond actually help this. They make the diamond sparkle so much. The princess cut, which is supposed to be like a squarish diamond, with all these little cuts at an angle and everything like that, maximizes this. Maximizes this total internal reflection. Cut crystal, if you have someone that has like a chandelier with the little crystals on there, the more kind of cuts in the crystal, the more this can happen, because you're basically trying to limit the opportunities for light to get out. You're trying to keep it be somewhere between the critical angle and 90 degrees. So this is our lesson on light. It's not everything that we normally talk about, but it's enough. It's enough to kind of get you through kind of some basics of life and how we operate. Next week and the following, next 2 weeks, we're doing some more labs. You're going to have about 7 options of different labs you can actually do. And next week you're going to pick one, the following week you're going to pick another one. So you're turning in, out of the 7, you're doing 2. The list of materials you'll need is actually provided to you in the overview document for this week's lesson. Other than that, I will see you guys next week.